Yes, I'm Vasileios. I'm a postdoc in Cambridge, and today I'll talk about PSLP. It's padded SLP automatic vectorization. This is the first automatic vectorization algorithm that we know of that can vectorize non-isomorphic instruction sequences. So this is joint work with Alberto from Edinburgh and with Tim Jones from Cambridge. So I'll get started with some introductory ideas. So why do we need vectorization? Well, vectorization gives us scalable parallelism. You can really understand what I mean by that if you compare vectorization, like vector parallelism, to instruction level parallelism. So this is how an ILP processor looks like. You have several functional units, and they all share a register file, and the access pattern to the register file is completely random. So any functional unit can access any part of the register file. So this requires hardware support. So this limits the amount of parallelism that you can get. So you cannot have a very wide issue ILP processor. Instead, a vector processor looks like this. So each lane of the vector unit is allowed to access a specific part of the register file. So this allows for much more scalable hardware, and therefore we end up with potentially higher performance and better energy efficiency. Okay, so it's of no surprise that processor vendors have been supporting SIMD instructions since a long time ago, even in commodity processors, everyday, like general purpose processors, and they have been updating the instruction sets ever since. So one problem is that compared to ILP, like in ILP processors, instruction level parallelism can be extracted efficiently at runtime. So there's hardware support that can extract ILP and run it efficiently. The problem is that vector extraction is not being done currently at the hardware level. So the programmer has to take the burden of writing the code in such a way that the programmer expresses this parallelism at the source level. So one solution is that, so let the programmer do all the work, or you can rely on a compiler that can efficiently vectorize the code. And this is what we are trying to do here. We're trying to improve the automatic vectorization algorithms by the compilers to let them transform scalar code into vector code much more efficiently. Okay, so our work is called PSLP. P stands for padded, and SLP is the super-aware level parallelism. It was first introduced in a PLDI paper in 2000. It is a straight line code vectorizer. It's been implemented in several compilers, including the open source ones, GCLVM. And in theory, it should be a superset of the loop vectorizer. So in theory, you could take a loop that's being vectorized by the loop vectorizer and unroll it a couple of times, give it to SLP, and let it do the work. And in theory, they should produce the same results. And also, even if the loop vectorizer fails, let's say you have complicated control flow that the loop vectorizer cannot deal with, the SLP vectorizer can still vectorize some of the basic blocks within the loop. So you could get some potential benefits out of that. In practice, though, the implementations of SLP are usually missing some of the features that are present in the loop vectorizers, and therefore their performance is not the same. So a lot of times the loop vectorizer is much faster, and sometimes the SLP vectorizer is faster than the loop vectorizer. It is common practice in compilers to run both. So you first run the loop vectorizer, and if there's anything that's not being vectorized, it's been taken care of by the loop vectorizer, by the SLP vectorizer. Okay, now I'll give you a brief overview of how the SLP vectorizer works. So the input is of course scalar IR. We first scan through the code looking for seed instructions. So the seeds are the instructions where we start vectorizing from. So these can potentially be any type of instructions as long as they are of the same type and there are no dependencies between them. But usually a good bet is to start from consecutive stores or reductions. Then we start building a graph. That each node of the graph contains the nodes that can be potentially vectorized. So these are the groups. Each node has a group of scalars that can be potentially put together and vectorized. And each edge is a data flow. So we build this graph, and once we build the graph, then we can calculate the cost. We can see which one is better. Is it the scalar code that is better, or is it the vector code that is better? And to do that, we query the cost model. So we ask the target, so does this instruction run how efficiently does this instruction run at this specific target? And the cost model replies to us, gives us some numbers, we add them together, and this is what the cost is. So after knowing the scalar and the vector cost, we compare them, and if vectorization proves useful, then we replace the scalars with vectors. If not, we just leave the code as it is. Okay, now some examples when SLP fails. Well, of course, we have data dependencies, like you have 3 adds and another add that depends on the previous one, then there's no way that you can place add over there. Then a more common failure of SLP is when you have too much gathering and scattering going on. So let's say you have these 4 adds that could be potentially executed in a vector form, but they are either let's say they're reading from the scalar side too much, or their results are being read by the scalar side too much. Then we need to emit, insert, and extract instructions. And so starting from 4 scalars, we ended up with like 9 instructions, and this, of course, is not beneficial. And finally, if you have non-isomorphism, let's say we have 3 adds and 1 multiply, then there's no vector unit that can execute this kind of instruction. And therefore, in these cases, SLP fails. And this is exactly what we're trying to fix with PSLP. We're making sure that we pad the code with redundant instructions to make sure that there's no such thing happens in the compiler. Okay, so I'll give you an example. We start with this very basic code. What it does is that it reads from array A, it performs some computation and writes back to array B. And we have to notice here, what you have to notice here is that there's an extra multiplication on the top. So once we build the dependency graphs, they look like this, and of course the first graph, which corresponds to the first statement, is bigger, so it has 1 extra node here, the multiplication with a constant. And I'll show you now how this becomes a problem with SLP. So we start from the bottom. So these are the seeds. The stores to B are the seeds for vectorization. So these become a group. So here I'll build the SLP graph, and over there I'm showing whether this group gets vectorized or not. So we start with the seed instructions. These can be effectively grouped together, and they become a vector. They can potentially become a vector. Then we follow the dependencies upwards, and we can see that these stores are reading from these adds. These are fine. So yes, the stores are aligned in memory, so they're fine. The adds are also independent, and it's fine to vectorize them. And then at this point, these adds are reading from a load and a multiply. So the SLP tries to form a group out of those, and the group has the multiply and the load. And of course, there's no such unit. You cannot execute that on the target processor. And therefore, the SLP pass will stop at this point. And let's see what cost we get. So in this example, I'll use a cost of 1 for each instruction, no matter whether it's a scalar or a vector. And So we have, initially we have a scalar cost of 7 because we had these 7 scalar instructions. And if we stop vectorization at this point, although we have saved two instructions by converting them into vectors, we still have a cost of 7 because we need to insert these scalars to the vectors. So we have 3 scalars, the two new insert instructions, and the 2 vectors. So the final cost of these, like the cost of the code, if we try to vectorize only these two groups of instructions, will be 7. So there's no benefit in vectorization. And if you try to vectorize these codes, it will not get vectorized. Okay, so PSLP fixes the problem of non-isomorphism. So we take the input graphs, we figure out that this multiplication is missing from the other graph, so we pad it in, so we add it onto the second graph, and at this point you have to make sure that the semantics are correct, and that's why we emit the select instructions. So a select instruction, we show the select instruction with this like orange kind of node. Its symbol is an electrical switch, which selects either the left input or the right input. And what the select instruction does is that it propagates to its output either the left input or the right input. So in this left graph over here, the select will pass the value from the multiplication right to the add. And on the other side, it will completely ignore this multiplication and it will propagate the load directly to the add. So if you generate this code and you feed it to the vectorizer, the vectorizer will be perfectly happy to vectorize it, and its cost is 5. So it's less than the cost we had previously. Okay.
One question,
Sure.
because, well,
Sure.
at least my intuition before you showed the example was that you would, for example, multiply by 1.
Yeah, I'll get back to that.
Operation.
Yeah, so that's an optimization on top of that. So we have a set of optimizations that we run on top of that, like some people optimizations that will get rid of the select instructions. So we have, our approach is to, this is a generic way of converting non-isomorphic graphs into isomorphic with the same semantics. And once you get those, then you apply a series of people optimizations that do exactly that. So they try to remove redundant selects. So in this case, yes, you can do this trick. I'll get back to that later on.
Back to the generic case, where do you take the flags for select from? Because you have to know which channels do you.
Yes, so it's fairly straightforward. So depending on how you pad the graphs, if you like, so in this case it's fairly straightforward. So you know that since you have padded this multiplication, you have to ignore it. So it's a fairly simple way of determining the flag for the select. Okay. Now, okay. So I'll briefly go through the structure of the algorithm. So it is the PSLP is basically a plug-in to SLP. So we are reusing most of its structure. Once again, we start looking for seed instructions. We completely reuse it's basically the same code. After finding the seed instructions, we generate a graph, but this time we generate a graph for each seed. So we're not generating this graph where each node contains like the groups of scalars that we can vectorize. Instead, we actually need each individual graph. So we need each individual data flow graph because we're operating on graphs. I'll get back to this on the next slide with more details. So after generating the graphs, we perform minimal padding. This is the critical part of the algorithm. So how do you get these graphs that look different and make sure that they look the same, they are isomorphic, you emit as little nodes or instructions as possible, and they have the same semantics. So this is the core of the algorithm. How do you do that? And then after performing the padding, then you evaluate the cost, like the scalar cost, the vector cost, and then the padded vector cost. And if we show that the padded cost is best, then you actually emit the instructions into the code. If not, then you basically fall back to vanilla SLP. So you generate the SLP graphs once again, and you check whether scalar or vector without padding is best. So the yellow boxes, like the highlighted boxes, are the ones that we have introduced into the SLP graph, and the rest of it is basically the same infrastructure. Okay. So this is how. Yeah. Now I'll talk about step 3. Like how do you? It's basically I'll show you what I mean by a graph for each seed, and I'll also show you what I mean by how do we do the minimal padding. Okay, so the top half of the graph of the slide shows a high level view of what we're doing, and at the lower half I'll show you I'll use a concrete example, so these specific graphs. So we start with G1 and G2. These are non-isomorphic, they're different graphs. And we'll use some graph theory to make sure that we convert these graphs into isomorphic graphs with the same semantics. Okay, so we'll use the minimum common supergraph to make sure that G1 and G2 become uniform. And in order to do that, we need to compute the maximum common subgraph. That's according to the literature. So the maximum common subgraph is the maximum subgraph of these input graphs that contain the same nodes. So if you look at these examples, the highlighted parts represent the maximum common subgraph of G1 and G2. So they contain the same nodes. So we have a load here, we'll have another load over there. We have like an add, we have another add. We have a store, another store. We have a constant, we need another constant. So this is the most computationally intensive part of the algorithm. But once you get that, it's fairly straightforward. So you express G1 and G2 as a union of the MCS and the rest of the graph. So we call them diffs. So if you get G1, it can be expressed as the MCS, the maximum common subgraph, plus the difference. We'll do the same for G2. And according to the literature, once you do that, it's fairly straightforward. So you get the MCS, and you basically join diff1 and diff2. So what we did so far is that we took two non-isomorphic graphs, and we have a generic way of converting these graphs into isomorphic graphs with wrong semantics. So what we currently did is that we got these G1 and G2, we made them look the same, but if you take a closer look, we have 3 inputs to the add. So the semantics are completely broken.
Okay. One question,
yeah.
Because even determining that 2 graphs are isomorphic is generally a hard problem. So
it is, yes.
How do you find the maximal isomorphic subset of the graph?
Yeah, so there are plenty of algorithms out there that do that. It is computationally intensive. It's a very hard problem. In this work, we used like a lighter version. So we use some heuristics to try to guess what's the maximum common subgraph. So yes, we haven't performed a full exploration of like a sensitivity analysis of how good an MCS algorithm you need, but like we just tried one. It kind of worked, and yeah, like it's for future work. Like we have to.
Have you computed any, highest bound of how many nodes, for example, can you process in a reasonable time?
So
we need to wrap the talk up really quickly, so we're going to do speed.
Oh, right. Okay. Okay. So so now we have like isomorphic graphs with broken semantics, and to fix the semantics, we have to emit select instructions to make sure that the code that we have padded does not break the correctness. So we use select instructions to do that. So in this case, we we ignore, like in this case, we ignore completely the multiplication, right? And in this case, we ignore like this edge, basically. So this is a generic way of getting two inputs, any two input graphs, and generate graphs which are isomorphic and have the same semantics as the input graphs. But we can do better. So if you take a look at the example once more, the technique that I just explained will generate these graphs. So this has the select over here. The only reason it is there is because we have to ignore the multiplication that we have just padded in. And we can easily get rid of that by doing, instead of multiplying by 7, if we just change the constant and multiply by 1. And we can do the same trick for any kind of, for any operation that can behave as an identity function. So you can not only multiply by 1, you can add 0, you can shift by 0. And so we came up with a set of people optimizations that tries to get rid of as many selects as possible. So yes, you can remove this kind of, in these cases you can replace the select with the operation by simply changing the constant, or if you are selecting between two different constants, you can remove the select and directly feed the constant to the successor. Or if you're selecting between the same nodes, then you can completely get rid of the select. So these are a set of optimizations, people optimizations that can be easily applied by a simple pattern matching and remove a lot of selects. Okay, so we just checked how often does, like not how, like in which cases the PSLP applies. So we found two major cases. One is when the code itself is non-isomorphic. Like if you have this code, some of the instructions, some of the statements have this minus over here. So the code becomes, the code is isomorphic, and with PSLP we fix this problem. Or a more interesting case is when the high-level optimizations destroy the isomorphism. So initially we had this source code, and the compiler was smart enough to realize that this is a power of 2 and converted that to a shift. So yeah, it was like we had a perfectly nice like isomorphic code, and then after high-level optimizations before the vectorizer, this was converted into that, and PSLP kicks in and fixes this problem. So yeah, so these are the two main cases where PSLP can help. Okay, so we performed our experiments using LLVM on a desktop machine. We ran some kernels and some benchmarks, and we evaluated these three cases. By O3 we mean O3 with the SLP, with basically both vectorizers disabled. With SLP we mean O3 plus SLP only, and with PSLP we mean O3 plus PSLP. So PSLP is of course an extension to SLP, so this is kind of a superset of that. Okay, so these are some performance numbers. On the left side we have kernels, on the right side we have full benchmarks. So the kernels give you some insights of how this technique works. In several cases, PSLP is the only way to vectorize this code, and in some other cases, SLP goes until some point it reaches non-isomorphism and stops. So with PSLP, we make it go even further. So this is common in these two cases. This is what happens in these two cases. In the first three, SLP doesn't vectorize the code at all. So the results from benchmarks are not as interesting. So yes, you do get some speed up, but it's up to like 1% or so. So it really depends on the coverage of the code that gets vectorized with PSLP, basically. So now I'll just show you how, what the coverage looks like. So once again, we have three cases. Yellow means SLP only, so SLP is adequate for vectorization. So if you just enable SLP, that region will get vectorized to its full length. Green means SLP reaches non-isomorphism and stops. So it is able to vectorize up until some point, but then it stops because it cannot go further. And blue means that without PSLP, SLP would fail. So, and we measured how many times each of these cases happens in the code when we compile the code, and you can see that we have a wide range of results. In some cases, PSLP was required. In some cases, it made SLP a bit better, and in a lot of cases, SLP was good enough. And finally, this shows what we get with the people optimizations that remove the redundant selects. So we started with isomorphic graphs with a lot of select instructions, and with the people optimizations we managed to reduce the amount of selects down to, like, starting from like above a little bit more than 20% down to 15%. So you can see here that the initial approach of padding the graphs does introduce a lot of selects, but there are some ways of reducing it down, removing some of these selects. So the selects are indeed overhead, and you have to remove them from the code. Okay, so to conclude, we proposed a vectorization technique that can vectorize non-isomorphic code, and we use some graph theory for that. We use the minimum common supergraph to make sure that we emit as few redundant instructions as possible, and we emit select instructions to make sure that the semantics remain the same. Then finally, we have some people optimizations that remove these redundant selects in order to reduce the overhead that they introduce. So we evaluated PSLP on a real machine, and we showed that it has a higher coverage than the vanilla SLP, and sometimes it performs better. So that concludes my talk. I'll be happy to take any questions.